Welcome to the last lecture of the Quantum Theory of Light course. I hope that we had a nice, let's say, course together, nice semester together. Today's lecture is given by Professor Dr. Hopefully soon will be Professor Frédéric Bouchard. Dr. Bouchard is a research officer at National Research Council Canada. His expertise is structural light and also, I would say, structured photons and quantum key distribution, quantum cryptography, among many other research activities that he does. So I kindly asked him to give a lecture about quantum cryptography, and he kindly accepted this. So today's lecture will be with him. Fred, the stage is yours. So thank you very much for accepting these.
Perfect. So thanks, Ibrahim. Yeah, so that will be the last course of the semester. So I'm trying to do something a little more applied. And I guess you've seen a lot of the formalism for quantum optics, and then that will be hopefully a nice application of all you've learned. So just to give you an overview, I've split the lecture in two sections. So first part on the formalism of quantum cryptography, and another part more on implementations to see how the experiments would look like. So in the formalism part, I'll start just with a general intro to quantum technology. Then I'll go to classical cryptography, then moving from classical to quantum cryptography through quantum cloning, quantum key distribution, which is the main protocol of quantum cryptography. And then I'll go through the math of how to calculate secret key rates and do security analysis. And for the implementations, we'll go through source, channel, detectors, what are the different degrees of freedoms to perform QKD or quantum cryptography, and then a few more quantum cryptographic protocols. So with this, let's get started. So first section will be quantum technology. So by the way, at any point, please stop me, interrupt me if you have any question or something's not clear. All right, so the way you can actually see most of the application in quantum technology is you start with quantum technology, which is really just any kind of application that is derived from principles like entanglement, the superposition principle. You can also have coherence. So this is what is known as well as the second quantum revolution, where you're sort of taking advantage of quantum weirdness and not just on because like the first quantum revolution is you first need to understand quantum mechanics to know how semiconductors work. So electronics technically is based on quantum mechanics, but the second quantum revolution or quantum technology, this is where you're getting sort of the weird properties of quantum mechanics, and you take advantage of them. And then this is usually divided into three big parts. So the first part is quantum computing. And this will include quantum computers, Schwarz algorithm, for example. You also have things like quantum simulation, where you can simulate quantum systems using quantum devices. The second one is quantum cryptography or quantum communication. Cryptography. So in this case, you have things like quantum key distribution or QKD. So this is the one we're interested in. But there's also things like quantum money. And that was actually introduced before QKD. Something else would be quantum secret sharing. Quantum secret sharing. So anything that has to do with privacy or if you want to communicate secret information that has to do with quantum cryptography. And finally, there's quantum sensing. And this is applications where you want to measure things in a more precise way. So for example, you want to measure phase shift. So there's something called noon states. So this is in quantum metrology as well, quantum metrology. So you want to use quantum states, things like entanglement or different kind of sensitive quantum state to measure things more accurately. So this is basically where quantum cryptography fits into this sort of new quantum technology field. And then we're interested in a specific type of quantum cryptography, which is quantum key distribution. So this sort of gives you an overview of what's going on. So before we talk about quantum cryptography, let's talk about classical cryptography. So, and let me know if I'm going too fast for the notes or something. So public communication, this is where you usually have two partners. So we usually call them Alice and Bob instead of saying person A and person B. Alice and Bob, and they want to communicate some information. And in public communication, you'll write some message. So for example, hey. So Alice will take that message, send it to Bob through a public channel, and then hopefully Bob will get the same thing. Hey, there might be some errors, so you might need to correct for these errors. The thing is, in general, there's no reason why there couldn't be an eavesdropper, which we usually call Eve, that can actually have access to that same message. So if Alice wants to communicate something private to Bob, there's always the problem that there might be an eavesdropper listening. So this is why we need cryptography. So one type of cryptography, one type of encryption method is called Symmetric Key Encryption. And this you might have heard of, also known as the one-time pad. And this is where Alice and Bob will meet up somewhere, and they'll generate a very long key of random bits, so random zeros and ones. And then they'll go their own way. And then if they need to communicate some message, they can always just take the message, add on top of that the random key, and then send that. So from Eve's point of view, this is completely random. But then Bob, when he receives the encrypted message, he can remove the key because he actually knows the key, and then he should be able to get the message, and this should be completely secure. So let's go through the steps. So first step, you want to generate a random key shared by Alice and Bob. And this is really important that only Alice and Bob have access to this random key. So second, Alice takes the message plus, I'm going to write this little plus here, random key. So this means modulo 2 random key. So when you're adding 2, so 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0. Okay, so let's make an example at the same time. So let's say Alice has a message which would be 0, 1, 0, 1, 0. Then let's say the key that they generated was, let's just come up with something random, 0, 0, 1, 0, 1. So you need the key to be at least as long as the message, and the key has to be completely random. So the encrypted message would then be 0. So you just have to add them up. 1, 1, 1, 1. Okay. So if you add something that has some information to something that's completely random, the result is completely random. So this encrypted message has no information about the message. So this is what Eve has access to. So Alice, so the third, Alice sends encrypted message to Bob. And then finally, fourth, Bob takes encrypted message minus the key. And then what we would get is, so let's do the encrypted the message. So 0 minus 0, that's 0. 1 minus 0, that's 1. 1 minus 1, that's 0. 1 minus 0, that's 1. And 1 minus 1, that's 0. So you do get back the message. So this is completely secure. But there's a problem with this protocol is you need the key. Key has to be as long as message. But then when Alice and Bob want to transmit another message, they actually need to meet again at some point and generate a new key. So this is not really practical because if you want to send a lot of messages, you actually need to generate new keys all the time, because this is called a one-time pad. Once you use it, you have to throw it away. And there's even a story, I think, apparently one-time pad in Russian isn't one-time pad. So during the Second World War, I think, some of the Russians started to reusing their one-time pads. And then once you start doing this, it's actually possible to get part of the message. So the Americans were able to break the codes of the Russian because they were reusing the one-time pad. So one-time pad, use it once, you throw it away. So you actually need a way to generate these keys when you have your two users in remote locations. So this is what cryptography is trying to do for you. So there's something called a public key cryptography. And the goal of public key cryptography is to generate secret key between Alice and Bob, but that Eve doesn't have access to. So the most well-known example is called RSA. And RSA stands for 3-person. Just going to write their name. So they came up with this protocol. So let me go through actually how the RSA looks like. So what are the steps, and we'll make an example at the same time. So you want Alice and Bob to be able to generate a secret key that's random that only Alice and Bob have access to. So this is how the protocol looks like. So first, Bob generates two keys, a private key, or let's write public key here, a public key, and a private key. Okay, so you'll see how these things look like. The public key will be used to encrypt, and the private key will be used to decrypt the message. So Bob keeps his private key to himself. This is private, you don't share it with anybody, but the public key you just tell on a public channel so that everybody has access to. So Alice now has the public key, and it's actually fine if Eve has the public key. And those are the steps of the RSA now. So first step, you choose distinct prime numbers. So usually call them P and Q. So we'll just P and Q53. And you keep those secrets. So they will be part of the secret key, of the private key. Okay. And in general, here I'm just taking two small numbers, but you want to take really, really large numbers, because as you'll see, it'll get harder to factor powers of prime numbers. So second step, you compute their product. So n, just P times Q. And then this is equal to that. N is public. So this will be part of the public key. So you'll say what n is, but not P and Q. Eve will try to guess P and Q from n, but that won't be easy, as we'll see. So third step, you compute a function lambda n, where lambda is the Carmichael function. So this is something in number theory. Carmichael function. You can look it up. But the point is, if you know P and Q, it is really easy to calculate lambda. But if you don't, then lambda is really hard to calculate. Easy to compute. Okay, so if you know P and Q, you can actually write this function in terms of P and Q. And just the greater common divisor, P1 minus 1, Q minus 1. Okay, so this is how the function looks like. If you don't know P and Q, then this is really hard to calculate. So if we do the math, 52, GCD of 60 and 52. Anyone knows what the GCD of 60 and 52 is? 4. Okay, so that's 780. And this is secret because it will be hard to calculate this. So Bob will calculate lambda n, but keep it secret. Okay, next step. You choose a prime number, prime e, where e is between 1 and lambda of n. So for example, let's take e equals 17. So e is public. And then finally, you determine d, where d, or actually, where d is in this equation here, mod lambda. Okay, so here you should be able to see that d is equal to 430. This is secret. Just to sum up, your public key is n and 17. The private key is, well, technically, private key will be p, q, lambda of n, and d, but actually all the information of p, q, and lambda of n is all incorporated in d, so all you really need is d. So as long as you keep d a secret, you can announce n and e on the public channel. And here's the point. To go from n and e to d, or the other way around, so this is easy, this is hard. So once you know the private key, it's easy to calculate the public key, but not the other way around. Okay, and then how the encoding works is you have a message, M, and you have a ciphertext, C. So the encryption looks like this. Mod n, and the decryption is the other way around. So how do you get the message from the ciphertext? That's CFD. So as you can see, the numbers that we've been calculating, they're actually the exponents here. So you can actually run this into our example. So if we have a message, let's say our message is this number 65. So the ciphertext will be sorry, 65 power 17 mod 3233, which is 279T. So Alice will take the message, which is 65, and then doing the encryption, the ciphertext will be 2790. And then Alice will send that on the public channel to Bob. And Bob, once he receives the ciphertext, he can get back the message by calculating this here. 65. Okay, so you can actually run the numbers. You'll see that everything works. So the only way to break RSA, really all you need to do is to figure out, is to find P and Q. That's it. Because you know N, so if you know N, all you need to do is find P and Q. And fortunately, there's an algorithm called Schwarz Algorithm that can do that. So here's what's going on. All of our
so for RSA, so you just use the same, you can use the same key over and over again, kind of as much as you want, essentially. Like you can just send one key and then encode every bit with.
No, I still think you need your key to be as long as your message, because if you start reusing your key, I think you can figure out what the message looks like.
Okay.
Yeah.
Cool.
But you're right. That's not it's not exactly like the one-time pad.
Yeah.
But I mean, you still need to generate some keys as you're making new messages. Yeah. But yeah, so the problem is right now, all of our, like when you're banking online or these kind of thing, if you're sending an email, most of your messages are encrypted using something like RSA. But actually, there's no proof that this is secure. There's no proof that factoring large prime cannot be done. So who knows? It could be that one morning some mathematician wakes up and finds an algorithm that's classical that can factorize products of large prime numbers, and then we're pretty much screwed, because the whole cryptographic infrastructure we have today will just fall. Or probably in a few years, when we have universal quantum computers, or just a quantum computer that can perform Schwarz algorithm, then most of our cryptographic infrastructures are not secure anymore. So this is a problem. And then, I mean, spoiler alert, the solution is quantum cryptography. Or there are other solutions, but the only real solution to this problem is quantum cryptography. Okay, so why would quantum cryptography solve this problem? So we'll go through the quantum cloning, or the no cloning theorem. So the no cloning theorem is probably one of the most important theorem in quantum mechanics in terms of information, or how information is encoded and decoded when you're dealing with quantum systems. So basically, quantum cloning, what you want it to look like is something where you start with some pure quantum state, and then you get two copies of that quantum state. So that would be quantum cloning. And then the proof for the no cloning theorem is really simple, actually. So usually how it goes is you say, okay, if you pick a basis, let's say you're in the 0, 1 basis, cloning a 0 qubit would look like this. Cloning a 1 qubit would look like this. So far, so good. There's no reason why this couldn't be done. By the way, I'm omitting extra ancillary qubits to do this. Okay, but the problem is, whenever you have an operation in quantum mechanics, you need it to be universal, so it has to work in different bases. So we can now consider a superposition basis. Then if we perform cloning, you would get something like that. But also, when you have an operation in quantum mechanics, you want your operation to be linear. So the cloning should also work not just on the whole state, but on the different components of your state. So you should have something like that as well. So individually, you should be able to clone the 0 state or the 1 state. But the problem is, you see, those are not the same. So there's no quantum cloning in quantum mechanics, no cloning theorem. This is essentially the no cloning theorem. So what that means is if I encode information on a quantum system, I cannot just make a copy of that quantum system and have that copy to be the same as the initial one. But in general, what can be done, this is allowed by quantum mechanics, is to generate two imperfect copies. So now I'm writing rows for density matrices. And usually how these density matrices will look like is something where you have your initial quantum state with some fidelity, but you also have sort of the orthogonal. Okay. This is essentially noise. Whenever you're measuring your qubit, you're getting some incoherent mixture of your orthogonal state. So, and in general, I can tell you for qubits, cloning fidelities will be something around. I mean, there are different types of quantum cloning machine, but you get something around 5, 6. Which means you can clone information, but they're not perfect. You're always going to get errors. And here the amount of errors will be something like 13%. Okay. So how does that translate to quantum cryptography? So let's go with D now, quantum key distribution. So if you have Alice and Bob, let's go with our same setting of just normal classical cryptography. But now instead of encoding the information on, an electric signal, you want to encode the information on a quantum signal. So the information will be sent using quantum state psi. You know that if there's an eavesdropper listening, say Eve is listening, two things will happen. So the first thing is Eve won't get all the information, because even if she's making the best clones possible by quantum mechanics, there's still going to be they're going to be good only 5 out of 6 times. The other thing is Bob will get errors. So not only Eve doesn't get all the information, but by getting part of the information, if she makes 2 clones, it's called one goes for Bob, one goes for Eve. So there's the incoming state, you make 2 clones, keep one, send the other one to Bob. You see that the information she's getting is not perfect, and Bob will get some errors. And then the whole point of quantum cryptography is to say, okay, well, if there's errors in the states that Alice sends to Bob when Bob is measuring it, something happened, and you have to assume there's an eavesdropper trying to get information about it. So qualitatively for quantum cryptography, if there's errors, that means there's an eavesdropper, that means it's not secure. If you have no errors, there's no eavesdropper, because it wouldn't be possible to get information without introducing errors. What's going on? Okay, no, all right. Okay, so the first protocol that was introduced is called BB84. So this stands for Bennett and Broussard in 1984. So you'll see for the names of protocols for quantum key distribution is usually just a bunch of letters and the year, so it's not really original. But the way it works is Alice will send photons to Bob, and here's how the encryption goes. 0 will go to 1. Oops. So there's going to be a first basis where Alice will generate a random key. This will be used for the one-time pad. And then if she gets a 0, she'll encode a state ket 0. If she gets a 1, she'll encode the state 1. Then you also want to do this in a different basis, the second basis, where you're going to say, okay, 0 will go to the state 0 plus 1, and 1 will go to the state 0 minus 1. Then Bob will do the other way around. Say, okay, if I measure a 0, I'll call that a 0 bit. If I measure a 1, I'll call that a 1 bit. And then if I measure in the other basis, call that state 0 and that state 1. Okay, and then if Alice and Bob would always use the same basis to encode, actually there it would be possible for an eavesdropper to just measure the state and then send the state to Bob. But the problem is, for the problem for Eve is if Alice and Bob are just randomly choosing what basis to encode the information in, then Eve doesn't know in what basis it's been encoded in, so half the time she would introduce errors. So this is the whole point of BB84 is you pick two bases and you randomly pick between them. And then whenever Alice and Bob pick the same basis, then they should have their shared key. But they have to do something called sifting, which is whenever Alice and Bob only keep keys when the bases match. Unfortunately, half of the time, Alice will prepare a photon, let's say in basis 1, but Bob will measure in basis 2, and that outcome will be completely random. So you just have to throw that away. And then, so that means if you actually look at how many bits of secret key you can generate per second, what you have to look at is the secret key rate. This is secret key rate. And if you have no errors, so K, if you have no errors, K will be equal to 1/2. That's because of the sifting efficiency. Let's see. And then R. And R here is the raw key rate, which is basically how many photons Bob is detecting per second. And that will tell you how many secret key you can generate per second. And then, for example, if Bob detects, I don't know, like 200 photons per second, you have to take into account the sifting efficiency. That means your secret key rate is 100 secret key per second, which means Alice would be able to send to Bob a message that is 100 key bits long per second. So the secret key rate sort of tells you what kind of secret rates Alice and Bob can communicate with. Okay, so now the question is, what if you have errors? And that's, I mean, qualitatively, you'd say, okay, if you have errors, then it's an eavesdropper. That means it's not secure. Close everything. Don't communicate. Because the worst thing that can happen isn't that Alice and Bob cannot communicate. That's fine. The worst thing that can happen is Alice sending private information to Bob or secret information to Bob where they think it is secure, but there's an eavesdropper listening. So yeah, if there's some errors, qualitatively, you'd say there's an eavesdropper, stop everything. But the problem is, most of the, like anytime you do an experiment, there will be some errors. So does that mean there's always an eavesdropper? So let's say you have 1% errors. You know, are you sure there's an eavesdropper? So that's where the whole calculation of secret key rates gets more quantitative, and I'll show you now how to calculate secret key rates. The secret key rates. And the whole point is errors means eavesdropper up to a certain point. And you want to know how many errors you can tolerate where you know it's not an eavesdropper. Okay. So when you have errors, the secret key rate will be this plus R. There's an extra factor. This is called the secret fraction. The secret fraction basically tells you if you have a key that's that long, what fraction will you be left at the end of the day that is secure and free of errors. And R is simply the difference in mutual information. Okay. So what this means is, so IAB, let's write it down here, is the mutual information between Alice and Bob. And then IAE is the mutual information between Alice and Eve. So what that means is, as long as the information that's contained between Alice and Bob is larger than between Alice and Eve, you should be fine. Your final key will be shorter because you have to do more stuff, but there you should be okay. But it kind of makes sense if it's the other way around. If Eve has more information about Alice's key than Bob does, there's no tricks that you can do that will give an advantage to Alice and Bob. So, so this is now how you can calculate the mutual information. So this is all in terms of information theory that was developed by people like von Neumann and Shannon. So there's a few useful definitions here that will help you to calculate the mutual information. Okay, so the H are entropies. The first one, when you have something like HA, that's a marginal or an individual entropy. And you can calculate the entropy of a key. So if all the keys are zero, if you have a bunch of bits that are all zero, the entropy of that is really small because there's basically no disorder. If you have a key that's completely random between 0 and 1, your entropy will be 1. And I'll show you how to calculate these things after, but this is basically it. Then you have the joint entropy. Now you have to consider the correlation between Alice and Bob's keys, and that will tell you what the entropy is. Then the other one I had was the conditional entropy. So this is where information theory meets quantum mechanics. So this is getting interesting. So in general, the entropy, you might remember this definition from your thermodynamics or statistical mechanics course. So this might ring a bell. This is the general expression. But there are two specific definitions that are useful. So there's Shannon entropy, which we usually write with a lower case h. And this is also known as the binary entropy, which is a specific case when you're only dealing with two values. So this is what you have with bits. That's X. And another one is the von Neumann entropy. This will be useful when you want to directly calculate the mutual information from a quantum state. So when you have a density matrix rho. So this is just now the generalization. So the sum becomes the trace, and then you have. Okay. So let's do an example of how you would calculate the mutual information. There's something called an eavesdropper technique, which is called the intercept resend. So this is a case where Alice is trying to communicate information to Bob. So it's a specific technique by Eve where Eve will basically measure the state that Alice is trying to send to Bob. And then whatever she measures, she'll just send that back to Bob. Okay, so what's going on there? And then what we're trying to measure is the secret fraction, which is IAB minus IAE. So since Alice and Bob are randomly picking their their basis, so either basis 1 or 2, Eve has a 50% chance of actually guessing the right basis. So half of the time she'll get the perfect information, the other half she'll just get random information. So you can kind of see qualitatively that her, let's write it like this. The Alice Eve mutual information will be 50%. Okay, so that's sort of easy to see. Now, what about the mutual information between Alice and Bob? So let's use this definition here, minus H conditional. So the first term, H of A, so what's the individual entropy of Alice's key? You can try to think what would that be. So since the key is completely random, the entropy will be 1. You could actually calculate that. And then how about the conditional entropy from Alice and Bob? So if Alice has a key and Bob will get a key at the end, depending on the number of errors in the key, that will dictate what is the entropy. So the entropy will depend on the errors. This is what we call Q. So I'm basically just using Shannon entropy for the conditional entropy. And then Q is the fraction of errors in their mutual key. And Q is actually a really important quantity in QKD or quantum cryptography. It's called the quantum bit error rate. Bit error rate, or QBER. And the definition is the number of errors in the key, in Alice and Bob's shared key, divided by the length of the key. So once Alice and Bob are done sending their photons, they actually need to call themselves on a classical channel and take a fraction of their key and compare it, just to try to understand what's the fraction of errors they have. Because you actually need to know what the quantum bit error rate, this value Q, is if you want to know what's the mutual information between Alice and Bob. So then, okay, what we want to know is whether the mutual information between Alice and Bob is larger than Alice and Eve. And here, let's try to calculate Q for this case. So there's 2 cases. So either Eve did a good job and guessed the right basis, and then there will be no errors in Alice and Bob keys. Or the other case is she guessed the wrong key. That means she measured in the wrong basis. She gets something completely random and then sent a completely random photon to Bob. And in that case, Alice and Bob's error rate will be 50%. So they have completely random bits. And the average of these 2 cases will be 25%. So that's the error rate that you get from an intercept resend. And if you calculate what Shannon entropy of 25% is, that's actually something around 81. So IAB will be equal to 1 minus 81%, which is 0.19. And you see this is already smaller than 0.5, meaning IAB is smaller than IA. So we know that there's no way Alice and Bob can generate a secret key if there's an eavesdropper doing an intercept resend attack. And this is because Eve is getting way too much information compared to Bob. So this is how you would calculate secret key rates. So the secret key rate, in general, you can write as this. So 1/2 for the sifting efficiency. In this case, 1 minus HQ, 1 minus 8. Okay. And then you see, whoops, oh no. I closed my surface, just a second.
Out of battery?
No, I just nudged it. Just a second. Yeah, that's not a good spot for the. No. It's not a good time to stop yet. Oh, no, wait. Okay.
It is up to you.
Sure, we can stop. Turns out I shut it down. Did I run out of battery? I don't think so.
So we can stop and having a break of 10 minutes and coming back again.
Wait, no, I'm good. I'm good.
Okay, good.
I'm good. No, okay. Let's take a break. I have to reopen Zoom.
Thank you very much.
Okay, so that's how. Okay, this is how the secret key rate looks like. Just to remind you. So one way to understand what's going on with the secret key rate is that you have this one term, which is you have your initial raw key that has some errors and that Eve has some information about. Then you have this term here, which is actually how much you have, what's the fraction of your key you have to give away to do error correction. So the first thing you want to do is to get rid of your errors, because if Alice and Bob don't have the same key, if they send a message one to another, there's going to be some errors in the message. So that will come at a cost, and the cost is exactly the Shannon entropy of the error rate. So that will shrink your secret key. So now there's no errors, but you know Eve probably has some information about your key. So you have to do one more step, which is called privacy amplification, and that comes at a cost. That is the mutual information between Alice and Eve. And then you get a smaller fraction. By the way, for BB84, this is sort of a special case. Mutual information between Alice and Eve has a simple form, and it's just HQ. So in the end, the secret key rate for BB84 has this form, 1, 2, R, 1 minus 2 HQ. So you see the amount you have to give away depends on the error rate, or the quantum bit error rate, Q. So if your error rate is really small, actually H of Q goes to 0. So if you have no errors, you can just keep your whole key. If you have some errors, you'll have to give away part of your key for error correction, then privacy amplification. Now the problem is if you have too many errors, what you see is you have to give away more than what you have. So in the end, your secret key rate will be negative. And what that means is even if you wait, you wait for a full year to try to get enough bits to get one secret key, that will never happen, because whenever you have that secret key, you have to give it away to do error correction and privacy amplification. So are those two things, error correction and privacy amplification, clear? So the first one, error correction, is completely classical. You just get rid of errors. But the privacy amplification, but that's just for BB84. Now the problem is, what if you have another protocol where what Alice encodes and Bob measures is different than BB84? What if you have some other constraints, some experimental parameters you want to take into account? So in general, you want to have a way to calculate secret key rates for a very general case. So I'm going to show you how you can do that now. So one of the difference is we're going to consider that instead of Alice sending a photon to Bob, we're going to assume there's a source of entangled photon where one photon goes to Alice, the other one goes to Bob. So this is exactly, this is equivalent. So this is known as an entanglement-based QKD protocol instead of a prepare and measure. So prepare and measure, there's only one photon. Alice prepares, sends it to Bob. But completely equivalent, you can have something where you have a pair of entangled photon. One goes to Alice, the other one goes to Bob. And it just makes the analysis a bit simpler. And in general, Alice will perform a measurement on her photon, and Bob will perform his measurement. And ZA and ZB are sets of POVMs. So ZA and ZB, so they're positive operator value measure POVM. And what that means is it's a set of, it can be projective measurements, it can be any kind of measurements that when you add them up, they add up to the identity. So you want this to be complete. So for example, BB84, what you had was ZA and ZB were half of the case this, and the other half, just going to call them plus and minus, but you know what they are. Okay. So this is how the analysis will look like. So row AB, so let's say ideal case. In an ideal case, you want your row AB to be a pure state. So a pure state, you want something like a Bell state. So here I'm just going to write the psi plus Bell state. So this is what you want. But in practice, you're going to have some errors. And your row AB won't be a pure state. It'll be some incoherent mixture of different states. And what we'll do is we'll say, okay, I have a mixed state, and all the other information that makes an overall quantum state pure, which is called the purification, we'll give that to Eve. So what that means, and you'll see, we'll go through an example. We're gonna come up with a pure quantum state that takes row AB, which is not pure, and it will purify it. Sounds a bit weird when you say it like that, but let's purify row AB. Okay, so what lambda is, so lambda is the eigenvalues of row AB. So all you have to do is write row AB in a diagonal basis, and then those are the eigenvalues. So I don't know if you've seen this in the course so far, but anyway. And then if you want to go from psi ABE back to row AB, you just trace over Eve. So you take the partial trace over ABE. Okay. So by the way, now I'm sort of going through the math of how to do security analysis. So that, like, if you're not so interested in that, you can just zone out because it'll get a bit math heavy. But then after that, the second part after the break will be implementation. So it should be less, yeah, more interesting. Okay, so let's go back with our formula. So the secret fraction is the difference between the mutual information between Alice and Bob and Alice and Eve. But we want to be more specific than that now, because we have specific row ABs and we have specific measurements. So instead we'll say ZA, ZB minus ZA. But we'll just leave Eve because we don't want to specify any measurement for Eve. We're just going to give all the information to Eve. Okay, so this can be rewritten using the formulas I gave earlier, like this. So in terms of conditional entropies, ZA, ZB, ZB. And this is known as the Devatak-Winter formula. Okay, and then if you expand that even more, what you get is you can write everything in terms of individual and joint entropy. Okay. Let's see. So I have that. Okay. So let me show you how rho ZAB would look like. So keep in mind that the ZAs are POVMs. So what you get in the end will be something that looks like this. So trace of ZAJ ZBK rho AB. Yeah. Okay. Then rho ZAE, that's another one we'll need to calculate. This is given by J. And then the partial trace over A, J identity rho AE. Okay, so I think that's everything. And then the last step is to say, yeah, we have this, that's the formula we had earlier. But we want to minimize whatever we get. We want to get the minimal value by looking through all the different rho ABs. So what you do, if you do an experiment, you have some experimental values. That doesn't mean you know what the entangled state of Alice and Bob is. So you have to write down a parametrized quantum state. So a parametrized density matrix that takes into account the constraints of your protocol or of your experimental measurements. And then you look at all the possible secret key rates that you can get that are consistent with your constraints. And then what you do is you're being pessimistic and you're saying, what's the worst key rate I get under these conditions? And the reason why you minimize is you want to give the benefit of the doubt to Eve to say, okay, she's probably doing the best that is physically possible, so we're just going to minimize the secret key rate under our conditions. And this is how you basically calculate secret key rates when you have more, if you have experimental constraints, or if you're doing this for a different protocol, your ZA and ZB will change. So let's make one example. And after that example, we can go to the break. So this is, we'll do the secret key rate for a 6-state protocol. So 6-state protocol is really just a generalization of the BB84, where you have a first basis, which is 0, 1. You have a second basis, which is 0 plus 1, 0 minus 1. But you have a third one now. And the important thing is actually, if Alice and Bob are not picking the same basis, they're actually going to get completely random results. So you need the bases to align. Okay, and the secret key rate for that, it's called 6-state. Okay, so you're going to get a factor of 1/3 now instead of 1/2, because the 1/2 was a sifting, because you only had 2 bases. Now you have 3, so you get 1/3, get R. Then you get a slightly different equation here. So now what we're going to do is we're going to go through the whole process of calculating secret key rate from the mutual information for this protocol. And now, actually, the reason why I picked this one is if you have all these measurements from the 3 MUBs, this is tomographically complete, which means these measurements are enough to tell you everything there is to know about the density matrix. So instead of doing what I mentioned earlier, which is what you would normally do is parameterize your density matrix and then minimize at the end, we're going to just assume a specific shape of our density matrix, rho AB. And then because technically this is a tomographic protocol, so we know how it should look like. And then we're going to directly measure the secret key rate. So let's do it. That will take probably like 15 minutes. I don't know. So let's start with psi AB. So call that 0. That's for our ideal case. So if there was no errors, this is what we would want our Alice and Bob's entangled state to look like. Okay. And then the thing is, we're just going to pick a specific basis, but since everything is symmetric, you could redo the whole calculation with basis 2 or basis 3, and you should be able to get the same result as long as the bases are aligned between Alice and Bob. But in general, you can go through the calculation and consider completely different projective measurements for Alice and Bob. Okay, so now we have to write down rho AB. So rho AB will basically be psi AB plus the identity. So the identity will give you terms where you don't have 0, 0 or 1, 1, which is when you have correlation, but also when you have anti-correlation. So you'll have terms like 0, 1 and 1, 0. And those are the terms you don't want because those are errors. Because if Alice measures a 0 and Bob measures a 1, that's an error because technically they should be aligned. And then you can work it out that the factors that you need are the ones here. Okay, Q over 2. So you have to make sure that your rho AB is normalized. So the trace of rho AB is equal to 1. And then you see if Q is equal to 0, you get back the original psi AB, right, 0. Then if Q is 50%, then it's just noise. Okay, so that's rho AB. Now to write this in terms of psi ABE, we need to diagonalize this because this is not in a diagonal form. So let's write them out. 1 minus 2Q. So I'm just going to write them out in terms of matrices. It'll be easier to see. Okay. So you see the two states here, these are actually already in a diagonal form. But the problem is the first and the last row, they're not diagonal. So what we'll do is we'll play a little trick and we'll write them in terms of orthogonal states. Oops. Sorry, don't. Okay. Okay, so that's the psi plus state. And then we'll also write it in terms of the psi minus. Okay. And then we'll keep the okay. Now we basically just need to figure out what are the factors that we need to put there so that rho AB is equal to whatever we had before. So I'll just give it to you here. So if you write these factors, if you calculate this out, you see that both of these lines are equal. But what we've really done now is that we wrote rho AB in a diagonal basis with psi plus and psi minus. This will be 0, 1, 1, 0. Okay. So now we can calculate the purification that we give to Eve. And as I mentioned before, you take the square root of the eigenvalues, psi plus. This is for AB, and 0 for Eve. One, 0. Okay, so this is the purification. That's the pure state that takes into account all the information that Alice and Bob have and Eve has. Rho AB is then simply this because rho AB is a pure state. Okay. So there's a few things that we'll need to calculate. So one of them will be rho AE that we need for the formula at the end. So this, by definition, is just a partial trace over Bob. Sorry. So what that means is, another way to write this is that rho ABE okay. So let's calculate this. So if we look at psi ABE and then project 0 on psi plus, that will give us the state in A, which is 0, and E. Okay. Oh, and there was a square root of 2. Okay. Then the same thing for psi minus 0, square root of 2, 1. It's Eve. At some point, I'll drop just writing down the subscript. Yeah, but you know, Q over 2. Okay, so you see the third term in psi ABE will go away because the B state is in 1, and then you get the final state, which is 3, E and A. And then you get basically the bra of this ket. So that's for the first term. The second term, 1 minus 3Q2. Get similar results. Q over 2. At that point, you get a minus sign now. Oops. Zero, 2. And then the bra. Okay. Oh, sorry. That's rho AE. Something else we'll need to calculate is rho E. That's just taking the partial trace over A of rho AE. So same thing now, but okay. So here's how it looks like. So for the 0 state, you see in the second term of rho AE, only the third part stays. We can write it directly like this. And then we have Okay. Minus sign. That's one. Okay. We can actually simplify this because the cross term will cancel out, because in your first term you have a plus sign, and in your second term you have a minus sign. So this is good for us because we can simplify this. That's how it looks like. Oops. Okay, so far so good. Does everything make sense to everybody? Okay, we're almost done. Well, sort of. Okay. So another state that we need to calculate is rho z AE. So as mentioned before, this is equal to this thing here. Okay, so ZA, there's two states. So the first one will be with 0. Okay, so if we calculate that, so what we're doing here is we're projecting the 0 state, which is the first ZA, onto rho AE, which is here. So you see you get the first term there and the second term. So that's what's going on. And then only the E state is left, like this. Okay, also the bra. And as before, we have this term. Okay, so that's the first term, and then we have same thing for the 1, 1. When we project over 1, 1 in rho AE, we only have the 3, 3 term left in the first term. Okay. So, but the important thing to get here, what we'll need is what are the eigenvalues of rho ZA E? And then obviously there's Q2, because they're already diagonal, but you also need to find the diagonal elements of the first of this part. And then if you just run that in Mathematica or something like that, what you'll see is it's 1 minus q over 2. And then for this one here, you also have 1 minus q over 2. So those are the 4 eigenvalues, which will be useful. Okay, we're getting there. The other state that we need to calculate now is rho ZA ZB. So from the definition, trace ZA ZB rho AB. Okay, so there should be 4 terms. So the first term is, well, let's write it in a different way. Let's write what? Okay, 0, 0. So one way to look at this is if we go back to rho AB. So we want to know if you take the state rho AB, which is here, and you project, and Alice project on 0, 0, and Bob projects on 0, 0, what state do you get? And then just from the first line here, you see you get 1 minus 2 q over 2 plus q over 2. So that should be equal to 1 is q over 2. Then similarly, you'll have, I don't really like to put it there. I'll put it in front. Okay, that's better. Okay, you'll get Q over 2. Those are the diagonal elements in the identity matrix. Q over 2, 1, 0. Then finally, Q over 2, 1, 1. Okay. So that's row ZA, ZB. You see it's already diagonalized, so we know the eigenvalues. And finally, the last one we need to calculate, I promise, is row ZB, which, as you know now, you just do the partial trace over row ZA, ZB, which means A row ZA, ZB plus 1. Okay. So first term, you'll get 1 minus Q over 2, 0, 0. You'll also get Q over 2 is 1, 1. And then the other one, Alice state is not 0, so you don't get anything there. And then for the 1, 1 states, get Q2, 0, 0. It's 1 minus Q over 2, 1, 1. Okay, then if you simplify this, what you find out is just this is a mixed state. A completely mixed state. So now we're done. We have everything we need to calculate the entropies now. Everything good so far? Good, okay. So here are the entropies we need to measure. That's one. That's another one. Row E, row ZA, ZB, row ZB. Okay. So for row ZA, ZB, let's go back up. Sorry, ZA, E. We know the eigenvalues, so let's first write down the formula for the entropy. ZAE log base 2 rho ZAE. So you see the log of a density of a matrix in general, that's not so obvious how you take that. But if you write your matrix in a diagonal basis, then the log of a matrix is just the log of the diagonal elements. So that's pretty easy to calculate. So now that we know the what the eigenvalues of row ZAE are, and then taking the traces, just adding them up, this should be easy to calculate. So the eigenvalues are Q over 2, Q over 2, 1 minus Q over 2, 1 minus Q over 2. So there's going to be Q over 2 log, let's do this, log base 2 of Q over 2. There's another one of them, so we can turn the Q over 2 just by Q. Then there's 1 minus Q. Since there's 2, I'm just going to remove the over 2 already. Q over 2. That's it. Okay. Good. So for row E now. Okay, row E, we have it here. So the eigenvalues, so there's 1 minus 3Q over 2. Okay. And then we have 3 times Q over 2. So 3Q over 2 log base 2 of Q over 2. Okay. What's going on? Okay. Forgetting a ZA, ZB. For ZA, ZB, the eigenvalues are, well, you have them there. Somehow my Q's look like thetas, but anyway. So ZA, ZB. So you have the Q's, and you have the 1 minus Q. Okay, then for the last one, well, we already know that it's a completely mixed state, so you should know this already, that well, the entropy of a mixed state is 1, but let's calculate it just for fun. So get 1/2 twice, so that's 1, log base 2 of 1/2. That's -1, so +1. Okay. Almost done. The secret fraction now is a function of Q, which we said is H rho Z A E minus rho E minus rho Z A Z B plus rho Z B. So first thing we notice is rho Z A E and rho Z A Z B are actually equal, so we can cancel them out. That's nice. Okay, rho H of rho ZB is 1, so we'll just bring that in front. And then we have minus H of rho E. That's 1 minus 3Q2. So we're already getting close to the formula we had in the beginning. 3Q over 2. We just want to turn it into a form that is that correct? Sorry, there's a over 2 here missing. Okay. Just want to write it in terms of Shannon entropy. So to do this, let's add and subtract this term. 3 and subtract. What you see, this is just trying to get the 3 of the 1, 2, 3, 4th term into the 3rd term. So by doing that, this is what we get now. Okay, this here we recognize as Shannon entropy. Oops. All right. Finally, the secret key rate will be 1/3 R 1. Sorry, that's minus, yeah. Minus H3Q over 2 minus 3Q over 2 log base 2 of 3. Boom. That's the secret key rate for the 6-state protocol. Interestingly, if you set the key rate to 0 and you try to find what is Q, you'll see that the error threshold for the 6-state protocol is 12.6. And this is a bit larger than 11% for the BB84. So what that means is if you have a system, a QKD system, where you have, let's say, 12% errors, you cannot use BB84 because you're over the error threshold. The only thing you can do actually is to switch to the 6-state protocol, which is a bit more inefficient because you have a sifting efficiency of 1/3 instead of 1/2, but at least you're below the error threshold there. So as you can see, you can sort of play with your protocols to optimize whatever your experiment is, if you have more errors, if you have less errors. So this is it. You can take a break. And then we'll go with the implementations, which is shorter. So it's fine that the break is not. Yeah. It was just to show you exactly how you would, like, just to see it made, how you would calculate any kind of secret key rates for any protocols. You would just change your rho AB and your ZAB and then just go through the calculation. Okay, good. Okay. So Yeah, by the way, before we start, was there any comments, question about the first section, which was more math heavy, which basically showed the formalism for how to calculate secret key rates for QKD? Good, perfect. So that was basically, if you look at the literature on QKD, it started with the BB84, basically gave the idea, and then it took a bit of time just to figure out how to use the mathematical tools to calculate these things. So a big part in the beginning was just looking at quantum cloning machines, what are the fidelities, and then they went with full security proofs. And then basically now today, a lot of the work is just figuring out new protocols to get better performance. And then once you have a new protocol, you have to do the security proof, and this is sort of how it's going. But anyway, so now we spoke more about the formalism. Now let's talk about the implementation. So how you actually perform QKD in the lab, and what are the details about the different elements. So the first part will be the source. So what I mean by the source is the photon source that you use. So Alice, in everything we've considered so far, we always said Alice encodes the information in a quantum state, which means in a single photon state. But in general, it's not that easy to generate single photons that have a bunch of properties that you'd want them to be. So you want to be able to generate them with high rate. So you want to be able to send photons, many photons per second. You want them maybe to have some spectral properties or temporal properties, spatial properties. So this is a whole field of research in itself, just getting good single photon sources. But let's look at a different type of source. So there's an ideal source, which really what we mean is a true single photon source. So a Fock state. And this is really hard to prepare, actually. Fock state. So a true, you click a button, you have a deterministic source where you get exactly one photon out, not two, not 0, 1. Yeah. So this is what everything we've done so far is considering this. What happens is in practice, that's not what we have. The first experiments have been done with a laser source. The thing with laser sources, as you probably know, they're a coherent state, so weak coherent states. So what people have done is take a laser, attenuate it up until the point where your mean photon number is close to 1, or actually lower than 1, and call that a sort of single photon state. So if you have a laser, which is a coherent state, which I'm sure you've seen in this course, this is the formula. Probably know it by heart by now. Alpha n squared of n factorial. Okay. Then as you know, mu is the mean photon number. Mean photon number. People thought, okay, if we take a laser, we attenuate it, set mu close to 1, that's pretty much a single photon source. Okay. But you might not always get this state. If you have something like a diode laser, you'll get something called phase randomized. You get phase randomized pulses, where from pulse to pulse, there's no phase relation between the different pulses. So you'll get something that looks like this. So you basically just get rid of the overall phase information. Okay. Oops. So now this is, you don't have a pure state in terms of photon number states. This is fine because you're getting rid of the phase information. This is equal to that. Okay. And it turns out that it's actually better to have a phase randomized source, because the relative phase from pulse to pulse, Eve can use that phase information and use it to her advantage. So if you if you use a diode laser or something that has a low coherence time, you already get, you don't have a phase relation between pulses. But if you use something like a better laser, like I don't know, like a TISAF laser or any kind of oscillators where there is a phase relation, in QKD, you would actually want to add a phase modulator that randomizes the relative phase between the different pulses. Okay, so those are two types of source. Another one, this one is quite useful, source of entangled photons. So there was a whole lecture about this last time using SPDC. So SPDC. So the state looks something like that. So we have two modes, one for Alice, one for Bob. Usually they're in two different positions or two different directions. And then you're generating these twin beams where so this parameter is proportional to the pump amplitude. Okay. So if you have a state coming from SPDC, most of the time you're going to get vacuum and vacuum. So this is not useful. But sometimes you're going to get a 1-1 state. And in that case, if Alice has the source to herself, she can keep one photon, measure it, and then send the other one to Bob. And in this case, just use the fact that she gets a click that tells her there was another photon. So this is called a heralded single photon source. Single photon source. So they give you, so this is better than a laser source because lasers they have Poissonian statistics. So this is better than Poissonian, but you still have higher order terms. So if Alice gets a click, it could be a 2-photon state. So it might be that she's sending a 2-photon state to Bob. So, but that's different than a single photon. And there are other types of sub-Poissonian source. And some of them have been tested in QKD experiments. So you can have atoms, molecules, color centers, so NV centers and diamonds or things like this. And also quantum dots. I should mention heralded single photon sources are not deterministic, but if you had a quantum memory, you could store one, and then it can be deterministic because you could have something where you can deterministically get your photon out of your memory, and that is sort of turning heralded photon source into a deterministic source. But the problem is efficient and on-demand quantum memories are not really a thing so far, or they're not easy to make in the lab. So okay, so what is the problem with these non-ideal single photon sources? It's a problem with imperfect sources. Let's have a look again at our secret fraction. So we're always going to use now the BB84. We're talking about the secret key rate for now. So again, this is error correction. I'm just writing IE, but that's the mutual information between Alice and Bob. Error correction, privacy amplification. Okay. So there's 3 cases. First one, if you get a 0 photon state, so because if you have a coherent state, some of the time it's going to be in 0, in a vacuum state, in a 1-photon state, or 2-photon state. So you have 0. Let's look at Eve's information. Eve has no information. So if you send a vacuum state, there's no information in there. Eve doesn't have access to this. So by the way, even if you have a perfect single photon source, you always have these events, but that's one case. Second case is if you have a single photon. So in that case, for single photon, the mutual information of Eve we saw for, or let's write Q1. For BB84, that's just Shannon entropy. And then Q1 is the error rate for a one photon state. But now what happens if we have two photons? Any guess? Let's make this a little interactive. Number between 0 and 1.
1/2.
Ah, close. No, 1.
Oh.
Thanks though for for saying something. Yeah, so basically, if Alice sends a two photon state, so we mentioned this before. There's a theme of Eve being this super powerful entity that has access to everything. So we assume she has access to quantum memory, a non-demolition measurement, which can measure the number of photon without touching the encoding part. So what Eve would do is every time there's a coherent state passing, she would measure the number of photons. And if she knows that there are two photons, she can take a beam splitter, take one of the photon out. So there's now information on both of them. She can store that photon into a quantum memory, send the other one to Bob, and wait to the point where they're sifting and they're calling each other, saying what basis they used, and then measure the other photon. And then she gets all the information, basically. So whenever you get a two photon state, Eve can get all the information. And her error rate will be 0. That's the error rate that she'll give it. So that's really bad for Alice and Bob, because what Eve can do is every time there's a photon, she can measure how many photons there are. If there's one, she just blocks it. So that's just lost. That's fine. If there are two photons, she take one out, send the other one to Bob. Alice and Bob will see no errors, and Eve will get all the information. So that was one of the things people started to realize. If you just use a laser source, you're going to run into these kind of problems. And this in general, so Eve is doing what's called a photon number splitting attack. Photon number. Does that make sense? Say nothing if it makes sense. Perfect. So, okay. So now let's look at how the secret key rates look like for different sources. So the first one is a true single photon source. Single photon source. This we already sort of saw. One of the things we'll do now is we'll write down explicitly what this R is, because we saw this before. K is equal to 1 big R R. And we never really mentioned what R is equal to, but R will be equal to nu S T TB eta. Okay, so what is everything? So nu S is Alice repetition rate. So that's basically the rate at which she sends photons out of her setup. T, that's the channel loss. So that's how many loss you have in the channel. So I don't know, this could be 50%, 10%, anything. TB, that's the detection loss from Bob. And finally, eta is the detector efficiency. Detector efficiency. So those are actual experimental parameters you would get in a real life scenario. So for BB84 and single photon source, this is your key rate. So if you have all these parameters, you can actually calculate what would be the kind of rates you would be able to get. And one of the important things we like to do is look at the dependence of the secret key rate in terms of channel loss. So what you see here is K is proportional to T. So if you want to go, and usually the channel loss will scale with distance in an exponential decay. So if you increase loss, your key rate will decrease linearly. So actually, that's not really loss. That's more like the transmission, but we just call it loss. Okay, so that's linear with T. So that's not bad. Let's look now at weak coherent states. Coherent states. That's attenuated laser beams. For weak coherent states, the R, big R, looks similar. And now we have to add mu. So mu is the mean photon number or the average photon number. So if you have to turn mu down to something like 0.1 photon, that means you're sending less photon on average, so you're going to get less key. Okay. One other thing that changes is the secret fraction. Let me just write that down, and I'll go through HQ. Okay, so Y1 is the fraction of single photon, which means n equals to 1 pulses, which means how many single photon state on average you get from Atlas. And if you have a coherent state, there's a probability, like that's one of the term we had up there, and that will tell you what is the probability of getting a 1 photon state or a 2 photon state. But Y1 is basically what's your probability of getting 1. And if you add up Y0, Y1, Y2, Y3, they should add up to 1. So what's going on here is Alice and Bob can only get keys when they have a 1 photon state, because if they have vacuum, they wouldn't get a key. So this is why we have that Y1 here. And then the other thing is the privacy amplification. So this term is privacy amplification. This term is error correction. Privacy amplification, you have to look at the 1 photon states, because those are the one where Eve will introduce errors. So you have this slightly modified secret key rate when you take into account higher photon numbers. So for weak coherent state, I'm not going to go through the math, but Y1 takes this shape. So, okay, so mu is the mean photon number. So if we write down the full secret key rate, which is equal to that, what you see is, well, let's write it down. 1 mu 2 t tb eta 1 minus h q. Two. Okay. And then what you see now, there's a T in the H, and we know that H is Shannon entropy, and there's a bunch of logs in there. So this is now, this is a bit hard to see what's the dependence of T over K. So we're going to assume a specific case of Q equals 0. So we're assuming we have small amounts of errors. So now we can simplify this whole thing, and then K becomes, by the way, I forgot an R here. Okay. So yeah, now K is equal to eta, and then there's that term, and the rest goes away. Okay. So now the question is, we have a free parameter mu, which is also missing. Sorry about that. Okay, we have a free parameter mu, and the question is, in general, it's not clear what mu should be equal to. You probably want it to be smaller than 1, but what you need to do in the end is to optimize your key rate with mu. So what you do now is you say, okay, what's the optimal key rate I can get out of changing mu? So what we'll do is take the derivative of K over mu, set that to 0, and what you'll get is well, all this stuff goes away. Let's call this 1 here minus mu t tb eta. That will be the optimal. Okay. So in an experiment, if you're using attenuated lasers, the optimal mean photon number is basically your overall loss or your overall transmission. So if you have, I don't know, like if you have a detector efficiency of 50%, you have a T times TB of 10%, then you're down to 5%. So you need a 0.05 mean photon number. So now let's look at what would that key rate be equal to, and this will be US mu opt T TB eta, and then you get 1 minus 1/2. That's 1/2. That makes sense. Oh, no. But we can put that in. I'm gonna write it down. Okay, because we have a mu there. Okay. Got another 1/2. Good. So that would be your secret key rate. So the result here is that for a weak coherent state, your secret key rate now depends on the square of the loss. So that's pretty bad. So that basically tells you if you want to have a secure key rate, or if you want to perform QKD, and you're not using single photon source, but you're using weak coherent states, that's what people used to do before, you're actually going to get a quadratic scaling. So that will limit even more your distance, especially when your loss scales exponentially with the distance. So that's not good. So that was a protocol that, well, before that, what this basically meant at that time was, well, we cannot use lasers. We have to use true single photon sources. So then there was a lot of effort in the direction of developing single photon sources for QKD, because we knew that this was not an option for QKD. But then someone came up with what's known as decoy state protocol, which basically allows you to get back a single photon scaling in terms of secret key rate while still using a laser. So that was a big step in terms of implementations for QKD. And the way it works is you vary your mean photon number varies randomly among the values will be 0, mu, and mu. That's vacuum. That will be your signal, and that will be your decoy. So the way it works is Alice will randomly change the mean photon number to sending vacuum, sending mu, sending decoy. Then Alice will measure, as usual, the error rate, the probability of measuring a photon. And then at the end, when they call each other to compare bases and these kind of things, they'll also compare the error rate when Alice sends a signal state, a decoy state, or a vacuum state. And in general, you can do this with only two, just with a signal and a decoy, or you can use more decoy states. I'll just make your experiment more efficient. but that's the most well-known, the vacuum signal and decoy state. And the point of this is, well, if Eve is doing this trick where she blocks single photon states and only allows 2 photon states to take one of them and measure it, you can actually see if there's something weird going on, because if Alice sends a photon, a signal state that is, let's say, has a higher mean photon state, mean photon number, and she sees that, okay, that one is usually more efficient than when I send a decoy state that has a lower mean photon number, and that one seems to be less efficient, then you sort of know that there's an eavesdropper there blocking the single photon state and only letting go the 2 photon state. So that's sort of a way to keep track of what's going on there in terms of number splitting attack. That's the conceptual way to understand a decoy state. The math gets a bit nasty, but basically by randomly changing your mean photon number, you're giving a hard time to Eve to sort of keep track of what's going on. And in that way, what you get is you get a secret key rate that will look something like that. That's when you optimize your mu. Eta 1 minus 2 HQ, where mu optimal is equal to 1/2. And then what you see now is K scales linearly with T. So that's good. Because now we can use lasers, which can be really cheap, which can be really small, or they're really easy to manipulate. All you need to do at the end is add an intensity modulator that randomly varies the intensity. And then this is as good as a single photon source. It's deterministic. You have much higher rates. That's one of the problems with single photon sources is it's hard to get high single photon, high rates. With lasers, you can go even up to a gigahertz if you want. So that's really good. So this is basically at that point when this theory paper came out for decoy state protocol, that sort of changed a lot of the application in terms of QKD experiments. And very recently, in the last few years, there was a new protocol called the twin field protocol. And the only reason why I'm mentioning this is they found yet another way, playing with the protocol, they can now get a scaling that scales even better than single photons. And this is also using lasers. The trick there is they actually you need Alice and Bob's. So this is in an entangled in a 2 photon setting. And then Alice and Bob lasers have a phase relation, and this basically is acting as a single photon instead of 2. So in that sense, you're getting the square root of the loss scaling. Anyway, so it's getting better. So this will extend distances by another factor of 2 since your decay is exponential. So this is about the source. So basically, you can still use single photon sources. You can use laser sources, but you definitely need to use a decoy state protocol if you want to have a good scaling. So that's for the source. Any questions? Oh, okay. Now the channel. So when you perform QKD, there are different types of channels. Probably the most popular one will be fiber links. Since we already have fiber networks used for classical communication, the hope would be you'd be able to reuse them for quantum communication. And the important parameter is T. So T is your transmission, and it scales exponentially, where alpha is the absorption coefficient. This is basically just Beer's law. And L is the distance. Okay. And in fibers, the minimal alpha is in the telecom, is in the telecom region. So around 1550. This is why all of the classical communication is at that wavelength. And that's using people, if there is anybody here working with fibers, it's the SMF28. And with that, you get something like 0.2 dB per kilometer. Okay. If you do the math, that means, well, okay, no, let's come back at the end. Okay, forget that. Okay, the other type of channel will be free space channels. Free space channel. In particular, you have line of sights. So that's literally if you have two set up at the top of two buildings, or you know, if you have people at some distance and you want to have a QKD link, you would use a free space channel. So that's in a straight line. And by the way, in this lab, in Ibrahim's lab, there have been some experiments done with free space channel. So that was, we definitely have some.
was one of the main PIs.
Yeah.
Just comment on these.
So we have, I mean, all I can tell you is you want to reduce noise, so you have to do it at night. So you have to shine lasers at the top of some campus buildings at night. It's pretty fun. So the absorption of air is a bit better than in telecom. So that's definitely a factor that helps. But you have other things going on. So geometric loss from aperture. Apertures. So you have the sender's aperture and the receiver aperture that will give you loss. You have just the divergence of the beam, because when you're going through long distances, any kind of optical beam will diverge. And then, so you can get some formula for the transmission that looks something like that. DL squared. So as you can see, it is also challenging to perform QKD in free space, but actually the main thing is turbulence. So turbulence from atmosphere, also known as atmospheric turbulence. This is characterized by something called Cn square. That's the sort of parameter that tells you how much turbulence you have. And this is one of the main challenges of performing QKD in free space, is you have a lot of turbulence. So you have to compensate for that using adaptive optics. Okay, so these are the two main free space QKD channels. So keep in mind that for realistic QKD systems right now, realistic is limited to about, let's say 30 dB. So with more dB, so with more than 30 dB, what happens is your signal is attenuated so much that your signal is on the same order as just dark counts or noise background that you get. And at that point, this is where your error rate will cross the 11% threshold. So basically what that means is if you have more than 30 dB loss, your QKD system won't really work. There are better systems that can go even up to 40 dB, but this is sort of a rough estimate. So in fibers, that means that you're limited to a distance of something like 150 kilometers. So that's not really long, actually. So that means if you want to establish a QKD link in a city, that's fine. You can use fibers. But if you want to establish, let's say, a QKD link between, Ottawa and Washington, if you want the prime minister and the president to have some secret messages or some secret key, that's too long. So you cannot use fiber. You cannot use free space, line of sight. Well, probably because there's the curvature of the Earth at some point, but yeah, it's not much better in free space. It's probably even worse. So people started to look at other options. One of them is satellites. satellite QKD. So the idea is, so we have Alice, atmosphere. So one of the things is, vertically, the atmosphere is not that big. If you, after a few kilometers, there's basically no more atmosphere. So that means you don't have absorption, you don't have turbulence, you do have divergence. So you do have the airs, the loss from the apertures, but what's going on? Atmosphere. But technically, all you need to do is get through that 5 kilometer, and then you should be good. So the idea is, I'm going to draw a satellite. If you want to go to longer distances, or just in general global distances, so from North America to Europe, what you could do is you would have the satellite coming on top of Canada. You'd send your photon there, have a memory at the satellite. Then the satellite goes all the way to wherever Bob is, and then shoot the photon back to Bob. And at this, in theory, you should be able to go to much longer distances. And people have been talking about QKD with satellites for a long time, but quite recently, in 2017, there's the Chinese group that sent a Chinese satellite. How do you write? 1 or 2 T's? 2 T's. Let's go with that. Yeah. They send the Chinese satellite, and here are some numbers. So they were able to get up to kilohertz secret key rates, and the distance that they had was something about 1,200 kilometers. So as you can see, this is at least 1 order of magnitude better in terms of distance compared to fibers. So if we want to have a global quantum network where you have secure communication between different users on a global distance, definitely satellites will be a big part of that. So this is why there's a lot of interest. And by the way, there is a project with in Canada to send a satellite up there, just slightly different from the Chinese satellite, but this is sort of going right now. That's ongoing research. And another type of channel, or another way to extend distances, is using something called quantum repeaters. So that was also proposed. Repeaters to go to longer distances. Basically, here's the idea. You have Alice and you have Bob. And then let's say you have your rho AB, a single photon source in the middle. The trick would be to actually split your total distance into smaller distances. So you would have something like, you can call someone Charlie, rho AB, rho AB. So you need more photons, but in the end, the distance the photons are going through is getting smaller and smaller. And what Charlie needs to do is something called a Bell state measurement. And the important thing about a Bell state measurement is you can swap the entanglement. So something called entanglement swapping. So if you have entanglement, that's your rho AB, that's your other rho AB. There's entanglement between these 2 photons, entanglement between these 2 photons. If Charlie makes a Bell state measurement, he can turn the entanglement back to these 2 photons. So this is essentially the same case as the first one up there, but your photons went through smaller distances, and you can keep breaking up your distance into less and less. with smaller distances, but you need more repeaters. And the advantage of this is that your secret key rate scales to 1 over n. So n being the number of repeaters you have. So the first case would be 1. The second case, that would be 2. But repeaters are tricky because you need quantum memories, and then you need to be able to do entanglement swapping in an efficient way. But that's one way to sort of go to longer distances. So that's repeaters. Yeah, so you need quantum memories. Which people are working on, but it's still not that easy to make a quantum memory. And you need Bell state measurements. Okay, so that's for the quantum channels. Let's go with detectors now. So we started from Alice, we went the middle part. Now for Bob. So whenever we say, okay, Bob measures a photon, you need something called a single photon detector. You need something that tells you, okay, I had a click, I had a single photon. Single photon detectors are characterized by a few different parameters characterized by. So probably the most important one is the efficiency. So eta, we already saw that. Detector efficiency. The other one that's important is the dark count rate. So you don't want to have a detector that gives you dark counts. And what dark counts are is basically you get a click when there was no photons there. So it's a false positive. False. Yeah, false positive. Okay, another important parameter is the dead time of the detector. And this is basically the time it takes to reset. So when your detector measures a photon or detects an event, there's a period of time where it is blind to anything coming. So what happens with this is it limits the rate at which Alice can send photons. So definitely dead time. The rate has to be smaller than the inverse of the dead time, which basically tells you how many photons per second Bob can measure. And then finally, another important parameter is the jitter, or timing jitter, and that sort of tells you the temporal resolution. So even though your detector can give you a really small signal or a short signal when it detects a photon, from shot to shot, that signal will arrive at different times. So within that time window, this is called the timing jitter, and it basically tells you how precise you can measure single photons. So let's look at different types of detectors. Types of detectors. It's probably the most popular one is silicon APD, so avalanche photodiode. Diode. Photodiode. APD. So this is typically used for wavelength ranges around visible, so 400 to 1 micron. Efficiencies are pretty decent. You can get even higher than 50%. Dark counts are usually not a problem. You get something like 100 hertz. And then timing jitter can be something like 400 picosecond or larger. You have for telecom wavelength, you'd use in-gas APDs. Okay. Wavelength, that would be for 1550. Efficiency. Usually the efficiency will be lower for in-gas APDs. Okay. Dark count rates are okay. So those are sort of the standard options for quite a while now. But recently, there have been some new developments, and you have now two new types of single photon detector. One of them is superconducting nanowire single photon detector. Single photon, also known as SNSPDs. And their wavelength range is good for 1550. Their efficiency is much better for the telecom region compared to in-gas detectors. They have really low dark counts. That's really one good thing. And their timing jitter can also be quite low. Why am I writing 10%? This can be 30 picosecond. Then finally, there's another type of single photon detector known as transition edge sensors, TES detector. And the big thing about this one, so it also works at 1550, efficiency of 60%, and so similar to SNSPDs, but you have photon number resolving capabilities. This can be really interesting for 2KD because you would be able to directly measure the photon number. So you could put that into your analysis and maybe you can get better results. So that's one of the things people started to look into, but not that many people have access to transition edge sensors so far because they're really hard to manufacture and you have to cool them down. Okay, so there's now any question for detectors? Sort of wanted to give you an overview of implementations. Okay, good. So next part is degrees of freedom. So we've spoke about single photons, how you measure them, how you detect them. Now the question is how you encode the information. So in the original BB84 protocol, they were talking about polarization. So whenever we said, okay, there's a first basis with state 0 and 1, and the second basis, state 0 plus 1, square root of 2, 0 minus 1, square root of 2. What we mean is, let's call this horizontal vertical polarization. We have polarization of light, which are good quantum numbers actually. So you can consider them modes of the electric field where you can populate them with photon number states. And then for the other basis, you would use diagonal and anti-diagonal. So this is a really popular way to perform QKD using polarization. The nice thing is you can generate polarization states just using wave plates and polarizers to measure them and to prepare them. So usually these are really efficient, they're very stable, and it's straightforward to perform something like BB84. So for free space, polarization is ideal because it's not affected by turbulence. In fiber, now that's another story because there's something called polarization mode dispersion. And it's basically whenever you have a fiber, you can get different group velocities depending on the polarization whenever you have symmetries in the fiber. And that basically can decohere your state, which will turn your pure state into a mixed state and basically just give you errors. So that's up to a point where if your fiber is too long, you might just get a completely mixed state at the output. So polarization is tricky in fiber. That's basically the point. Another degree of freedom that's really popular is time bins. So in this case, if we take the example of BB84 again, you would say, okay, now my state 0 and 1 corresponds to having a photon at time 0 or a photon at time 1. And you would have something like this as a function of time. For the superposition, you basically just need to make superpositions of time bins, which are usually referred as phase states. And what this looks like is something like this, where there's either in phase or out of phase. So they're a bit more tricky in terms of generation and detection. Okay. So the surface is getting slow. Okay, generation and detection. So to generate these kind of states, you need phase modulators to control the relative phase between them, or intensity modulators to carve them out. You also need delayed interferometers to to measure the relative phase. Because when Bob gets a time bin state, the question is how do you measure the relative phase between two time bins? And the easiest way to do this is by using something called a delayed interferometer, where you split your photons into two paths. So basically you have time bins, you split them, you shift them because you have a delayed interferometer, and then you look at the event where they interfere, and that gives you their relative phase. In free space, it's not affected by turbulence. So because you encode your photons on a time scale that's much faster than turbulence. By the way, turbulence is more on the millisecond, microsecond turbulence, not affected by turbulence. But multi-mode interference, challenging. So basically, you have an interferometer here. Spatially, when you go through turbulence, you get your spatial mode now becomes very multi-mode because of the turbulence, and it can be tricky to have these interferometers and measure time whenever you have turbulence. So challenging, but still you should be able to do time bins in free space. For fiber, it's great. So you can just send your state through fiber. Even if the polarization changes, that doesn't really cause any decoherence in the time bin. So this is really one of the most popular degree of freedom for fibers. Okay. Spatial nodes. That's one of the favorite of the group in Ottawa, spatial nodes, where you can encode the information in the transverse degree of freedom. In particular, a popular encoding is using orbital angular momentum, also known as OAM, of light. And what this is basically if you have a transverse phase pattern that looks like e to the I L phi, L is an integer, you can turn this into a quantum state that's labeled with L. And phi is the azimuthal angle, the transverse azimuthal angle. Okay. And the reason why this can be interesting is you can actually extend these protocols to higher dimensional QKD, so high dimensional QKD, where instead of only considering qubits, you can also consider qdits. So now you're not just dealing with zeros and ones, but you can actually deal with 0, 1, 2, 3, 4, you know. And then, okay, detection of OAM and generation. You can use spatial light modulators to shape light modulators. You can use some liquid crystal device called Q plates. And for the measurement, you want something called a sorter. For people working in, with spatial nodes, those are all devices that they're probably familiar with. The problem is in free space, spatial modes are very challenging because of turbulence. Because the turbulence will directly change your spatial mode, which means now you're changing the quantum state that you're encoding in. And in fiber, this is also possible. So it has been done actually in different labs and also in Ibrahim's lab, but it is challenging because of mode dispersion. Okay, let's go through two more. So frequency bin. So that's another way you can do QKD. One thing that's popular is to use frequency combs to pump a crystal to get entanglement in frequency combs. Frequency, you can also extend this to high dimensional QKD, just like spatial mode. And by the way, you can also do this with time bins. Gen and detection. So to manipulate, you probably need things like gratings. And the problem is if you want to shift frequency or if you want to play with frequency, you always need nonlinearities. So frequency is a bit more challenging compared to other degrees of freedom. So you don't see QKD done in frequency so often. The last one is continuous variable QKD. Continuous. Just getting more popular. The idea is you encode the information, in field quadratures. So if you remember phase space, you have your X and P. If you have a coherent state that's rotating around your phase space, you can actually decide a position in phase space, and that you can actually use to encode the information. So maybe your coherent state is at that position, so that X and P or that X and P. So that's another way to encode information. The big plus of CVQKD is its simple generation, because all you need is a phase and an intensity modulator. And the same thing for detection. Detection is pretty easy. You don't need single photon detectors because you can do this with homodyne detection. So the hope is you can use sort of standard classical communication devices and not change things too much and still perform QKD. One of the problem is there's no security proof. So although people they think it's secure, there's still no security proof for this. All the other discrete variable protocols have security proofs, but not this one. Other problem is loss tolerance. So since you're encoding the information in the quadratures, if you have loss, that's actually changing your quantum state directly. So loss tolerance, so probably somewhere less than 20 dB. So it's less tolerant to loss. Good. Okay. So I had one more section, which I basically won't go through, but I'll just name all the protocols. So since I'm running out of time. So I had this section where I was going through all the protocols, showing what is the key rate, what is the error threshold, what are the advantages, disadvantages, what I mentioned. But instead, I'm just going to list them, and you can look them up. B92, so that one is Binet in 1992. You had SARG 04, which is 4 Swiss guys in 2004. You have something called differential phase shifts protocol. Differential phase shift protocol. Measurement device independent. This one is popular because you can actually turn all the security problems from your measurement devices to an untrusted user. It's independent. And finally, the most recent one is the twin field QKD, which I briefly mentioned. Okay, differential phase shift. So you can look them up. Those are sort of important QKD protocols that people are looking at. They all have their advantages in different conditions. But yeah, I don't have enough time to go through them. I guess I was afraid of running out of material, but yeah. Yep, that's pretty much it. Do you guys have any question, or should we stop the video?
I can stop the video. So just only one small comment, Fred,
Yep.
regarding to the CV QKD. Oh, let me see. Oh, yeah, good. So I was in a meeting with a couple of scientists, expert in theoretical scientists, expert in this. They say to me that during last 3-4 years, there have been serious progress in security proof for CV. And one of them claimed that, yes, they have the security proof right now. I mean, you are totally right. It was a challenge until even that time that I think it was almost 18 months ago, which I didn't know about that. So I don't know really the reference. Maybe I have forgotten to contact, or maybe he sent it to me. But this is what I heard from one of the experts.
Yeah. So I mean, it was sort of the general knowledge that, you know, eventually there will be a security proof, but at the same time, in conferences, whenever people spoke about CV QKD and you have someone from discrete variable QKD, they would always say like, yeah, but you don't have a security proof. We don't even know. But yeah, but I mean, most likely it is. So I'm not aware of anything published yet, but I mean, most likely it will.
And just for the people, how many people they know how radio works? Oh, okay. So this is exactly look like a radio. I mean, this continuous variable QKD is you have an oscillator, you modulate it, and what you have it on the other side, you have a homodyne or heterodyne detection. And what is happening, then you can have a local oscillator there and extract the information. That's all. So I will stop the video. Thank you very much, Fred. It was very informative and elegantly structured. Thank you.
Thank you.
Let's do.